Now we consider a very interesting application of the divergence theorem. The three-dimensional case divergence theorem, that is the Gauss formula. This is a flotage law of Archimedes. Okay. Ancient Greek mathematician. It says that an object, you put an object in some liquid. Suppose the density of liquid is low. So an object omega putting on some liquid which density low. So we want to compute. We want to determine the flotage of this object. Okay. The Archimedes flotage law says that the flotage is exactly equal to the weight of liquid of the same volume of this object omega. We prove this result using divergence theorem. Take a point P. Suppose that the coordinate is x, y, z in the boundary of from the boundary of omega. That is this point. This point here is our P. And we take a surface element d sigma. Surface element denoted by d sigma about P. That is a small pieces of the boundary surface. The boundary of omega is a surface. Now we take a point on the surface, on the boundary. Then we take small pieces of the boundary surface about this point, containing this point. Then in these small pieces, I draw in blue in this picture. This small blue segment is our d sigma. Okay, d sigma. So in these small pieces, we can assume, because it is very tiny, we can assume that the pressure of the liquid is a constant, and we can use the point at the point P to represent this constant. Therefore, the pressure due to the liquid at the point P is denoted by capital P. By the pressure law, because the our coordinate system is like this. The level surface of the liquid is xy plane, and the vertically downward direction is the z axis. Therefore, if the point, the coordinate of the point P is x, y, z, then the dip here is exactly z. So at the under the water, under the surface of the water, z, the pressure is rho gz, rho gz. Okay, rho gz. So the pressure is rho gz. So the force, the pressure here on this small at the point P is rho gz. We might assume that the pressure at the small pieces of surface d sigma is also rho gz, because d sigma is very small. Okay, so the force generated from this pressure, the force acting on these small pieces of surface d sigma, the force, pressure force, is F. F is a vector. As a force, it has a magnitude and also has direction. The direction of F is the inward normal direction at this point. That is, the direction is minus nu. Nu is the outward unit normal vector. The direction is minus nu direction, and the magnitude is the pressure multiplying the area. The small pieces is the area of the small pieces is denoted by d sigma. So this F is minus P mu. Mu is the outward unit normal vector, but F is pointed inward, therefore we have a minus sign here. Then multiplying the area of the small pieces, and this is minus P rho Gz, and this part using our previous notation, we also denote this by vector form of maybe we don't need this. Okay, we avoid this. Okay, so we copy this here. So this the flotage is caused why an object in the water will gain a flotage upward, because of this force capital F. But the horizontal component of this capital F has no contribution to the flotage. Only the vertical upward component has contribution to the flotage. So the upward component of capital F here we denoted by small df. The d here means very small, corresponding to the small surface element d sigma. Very small, corresponding to a very small area. The quantity we denote by df. Df is the delta f, the increment. But when the object is very small, we write it as df, infinitesimal small increment or change. Okay, so we use df. So df is the upward component of capital F, but the downward unit vector is k. Okay, it's the unit coordinate, the third unit coordinate vector, that is our k. Therefore, the upward unit direction is minus k. So df is the inner product of capital F, which is minus k. So df is f minus k, because our z-axis is pointed downward. Then this is rho gz, and I have no place to write. What should I do? I have to write in the next page, next line. Okay, df is f inner product which is minus k. Therefore, this is rho gz k and nu. Okay, f is minus rho gz. So rho gz is here. F is here. So minus rho gz and minus k. So that is minus is positive. Therefore, we have rho gz here. And then the inner product of k and nu. And we also have a d sigma. So this quantity is the upward components force. Okay. So all this df, this is the corresponding to the surface element. If the point P, if our point P goes through all the boundary surface of omega, then at every point, every small pieces of element d sigma, you have the df. all the df summing up together is just the flotage acting on this omega. Okay, so the total flotage should be the integral over the whole boundary of df. That is rho gz k inner product with nu, then d sigma. Now we applied the divergence theorem. This will equal triple integral of the divergence of rho gz k, then volume integral. Okay, but rho gzk, what's rho gzk? Rho gzk, because k is 0, 0, 1, so rho gzk is 0, 0, rho gz. So the divergence of rho gzk is the partial derivative of 0 with respect to x plus 0 with respect to y, then plus rho gz with respect to z. Rho and g are constants, therefore the divergence is rho g. Okay, so the result is rho g dv, therefore is rho g volume of omega. Then this quantity is the weight of the water, is the weight of the liquid having the same volumes of this object omega. So this is exactly the Archimedes law about flotage. Okay.